So here are real images taken as far back as 1987. As you can see in the top frame here, there is this 1,000 Jupiter radii cloud, which is extending out to 1,000 Jupiter radii. It's all atomic sodium, and you can see this from the Earth. If you just attach a sodium filter to your wide field camera or your spectrograph, then you look in 70 Jupiter radii. Okay, it seems that there's more structure. Seems like these concentric rings that are rectangular in nature. It seems that it's locked in some kind of either some kind of centripetal fashion or just something that is along the plane of rotation. And lo and behold, when you zoom in on the bottom on a scale of 15 Jupiter radii, you see that this emission is coming from one tiny moon of Jupiter, Io. There's a cloud on the right-hand side, as you can see, that's directly emanating from Jupiter's moon Io. And on the left-hand side, you can see that there's a stream of sodium that's independent of the location of Io. And that is absolutely outstanding, I'd say. Because why is that? If you look at this, on the top frame, you're seeing atomic sodium. In the bottom frame, you're seeing ionized sulfur and oxygen. Now, if you're, well, I think most of you are in India time, so you've had your cha and coffee, and it is evening, so maybe you'll be a bit tired. But what you can notice on the bottom is that there's gyration occurring. Now, this is due to the magnetic field of Jupiter. And
sorry,
yes,
could you please explain to us what exactly are we seeing here in this GIF, this video?
Yes, thank you. Right, so the top frame, what you're seeing. So let's see, before I play anything, the top frame is atomic sodium. And on the right-hand side, you can see Io. So Io also has resonant reflection from the sun. So it's very bright and saturated. This is taken by Nick Schneider in 1995. It's a vintage photograph, but taken over 15 nights. So we got very lucky. So you're seeing a sequence of images taken at 15 nights, and it's following Io. And so on the top panel, you can see that the sodium has a cloud and sort of structure also.
So this is a series of images in sodium, narrowband filter.
That's right.
Okay.
That's right. It's at the same wavelength, just to go back. It's at the same wavelength as this, the doublet, which is at about 589 nanometers. So that's at the top frame. But on the bottom frame, there's two other spectral lines, also narrowband filters, of ionized sulfur at about 636 nanometers, and then oxygen, ionized oxygen. So what you're seeing is a plasma torus, that things that escape from Io.
So is that the doubly ionized oxygen line at 5,300 or so?
Right. There's also the doubly ionized line. Okay. There's I think several. So some, depending on the night, you won't see that doubly ionized oxygen, but it has been seen. Here it's mostly, I'd say, sulfur, ionized sulfur, which is in the upper 600s.
Okay.
So what happens, what's phenomenal here is you can see the gyration of Jupiter's magnetic field because it's tilted with respect to its rotation axis. So the sulfur is neutral. So you can see it just rotating along with gravity. But here, with the electromagnetic force, you can see the ions gyrating. So when you put it together, you can see on the right. So on the left frame, you can see Europa, Jupiter's second largest, the second moon of the Galilean satellites come in, and you can see how these are rotating around. So you can see this gyration. If you especially look on the left side of your screen, it's very interesting that you're getting sodium emission even when Io is not in the frame. So perhaps looking for an exomoon that's emitting sodium might not be a bad idea. So modeling alkaline metals at exoplanets. So we have two models, call them Dishum and Prometheus. Now, Dishum, desorbing interiors via satellite heating to observe outgassing model. Now, This is a model that I've developed over the last few years in regards to modeling atmospheric evolution. So you can see in the first frame, you open up the planet, you calculate the actual energy dissipation, then you calculate the mass loss to the surface, then you calculate the atmospheric evolution, dNdt, and then you calculate what the line of sight column density will be due to the mass loss after you calculate the atmospheric evolution. And you can do that also for Europa here. So whether they're alkalines, so like sodium and potassium, I showed this as red, or water molecules such as O2, hydroxide, peroxide, water. So it can be applied in the solar system and outside the solar system. Something more detailed like molecules, which is very tough to detect at exoplanets in this regard, or atoms. I'd say sodium and potassium are relatively easy to find. And just to explicitly write that out, you can see that DEDT, DMDT, DNDT. So it's just a semi-analytic atmospheric evolution model. And that's the basis of the calculations and the predictions. Now this is fed into a radiative transfer model that my student Andrea Gebeck developed and recently just accepted for publication a couple months ago. And it's a spectrum simulator. This is, let's say, the field of exoplanet atmospheres, that you have a grid here, and usually most of the field only addresses that yellow blob you see in the center. Now this is the atmosphere of the exoplanet. But here we've added something new, the exosphere of the exoplanet. So you can see this red horizontal line that's like a torus is sort of an envelope around the gas giant. This is a torus, a ring forming around the exoplanet. And this is what we call evaporative transmission spectra. The idea is that the exoplanet is evaporating, and so when you view this in a spectrum, it's not necessarily just a static hydrostatic atmosphere that one is observing. So one thing to assess that is these optical depth profiles. So here these profiles reveal that, let's see, I'll go back, actually reveal that canonical hydrostatic atmosphere cannot be the only solution. So if you look down, following the blue line downwards, these blue lines are the canonical atmosphere, and you can exaggerate it by arbitrarily heating up the atmosphere by a factor of 10, just seeing, okay, what happens to my exoplanet if it's 10,000 degrees, which is a bit hot. And you can see that you can extend the atmosphere, but the question is, does that atmosphere stay neutral? Now the same process you can ask for these red lines. Here you can see the torus, also the escaping in cyan, and then green for an exomoon. And these are various ways we can assess the column density and the optical depth of these solutions. And the question is, does it stay neutral? So that question can be remedied by the fact that we have a plasma torus that will result in recombination of ions. So if you have a lot of ionized sodium, it's possible you can recreate neutral sodium even far away from the planet. And the key is really the magnetic field and the ionization. So as the title implies, alkaline exospheres of exoplanet system. So what is an exosphere? Exosphere is this tenuous gas that can be escaping from the planet or just embedded in this interplanetary medium around the planet. So here we did just a very simple chi-squared analysis, and you can see the best fit solution is something a gas that's moving at 10 kilometers a second and has a corresponding mass loss rate, about 1 billion grams a second of sodium being lost. So this is actually one way to link atmospheric escape and radiative transfer. So you can put these mass loss rates into your radiative transfer model, and this gives the sort of dynamism, a dynamic way to look at spectrum. So once again, we call this evaporative transmission spectra, and I think that should be what should be evaluated in every exoplanet atmosphere. If you read a paper, even in front page, and it comes out and it says, all right, we find water in this exoplanet. And if this exoplanet is orbiting 10 stellar radii away, I would ask, well, is this water evaporating or is it sitting still? So I think it might be, in my opinion, more reasonable to look at the evaporation signatures first, because these are not Jupiter-like systems. These are hot Jupiter-like systems. The gas is escaping very fast.
Apurva, there is a question from Saurav. Saurav, please go ahead.
So Apurva, can you talk a little bit about the chemistry that you need to assume for these collecting all the DNDT and column densities for all these molecules? And there must be some composition, some chemistry that you are assuming there.
Right. Yeah. Thank you very much for that question, Saurabh. Yeah. So let me just see where I have here. Okay. Yeah. So I can talk about the chemistry. Let's see if there's a better slide to show that, though. Probably. Well, it looks like maybe here. So here we just assume that this is atomic sodium, but the assumption and that most exoplanet atmosphere people make is that so if you see that bottom concentric circle, the H2 here, the assumption is that it is solar abundance. So the standard assumption is that if the sodium is coming from the planet itself, endogenic, then it must be at solar abundant. Now, that assumption can be tweaked. One can say, well, for some reason, I think this is a supermetallic star or a supermetallic planet. There's various models that can reproduce that, which is good. And you can have 10 times as much sodium than a G-like star or sun-like star. Now, you can push this model to 100 times as much atomic sodium and get a lot more in. But you can't, for most reasonable assumptions, put 1,000 times as much atomic sodium because of constraints due to planet formation. Just the amount of silicates that can be embedded in gas giants, this cannot exceed a certain factor. And the number seems to be roughly 100. This is an analysis by Thorngren and Fortney at UC Santa Cruz, 2018, I think. So
I was also confused a little bit about how we know about the stratification of the different molecules or atoms. So because I mean, most of the outgassing for gas giants is probably coming from some part of the, let's call it envelope, and maybe not from the core. And so there may be abundance differences between the core and the envelope. And it's maybe you can comment on that, how you model that.
Absolutely. Yeah, thank you. That's what I was referring to, that study by Thorngren and Fortney. That's actually for the envelope. It's for the atmosphere. And so that 100x solar abundance model is mostly for the envelope. So the core, yeah, definitely nothing is, that would maybe bump up the solar abundance by maybe a few more factors, but it's just coming from the envelope. And the way we usually model it is just like a free flow hydrodynamic escape, a good, so I call it a hydrodynamic wind. By the way, this figure that you're seeing here is motivated by the first atmospheric escape model for exoplanets by Ruth Murray Clay in 2009. Seminal paper. I encourage everyone interested in exoplanets to check it out. But here, also modeled as a hydrodynamic wind. So these days you can use something called energy limited escape to approximate this escape. And this way you don't need to worry about that stratification because you assume everything is just flowing out together. But it turns out you can actually worry about the stratification and model each atom escaping individually. But especially in the systems we're analyzing, that escape would be even less. So the static assumption, or even in the planetary assumption, actually does not fare as well as an exogenic assumption where things are outgassing. Hope that answers some questions.
Yeah, thanks.
Yeah, so great question. And that actually will bring us to the next part where we finally look at how do these models actually compare with each other. So planetary model versus a lunar model. So I'd say the implication here is that, yeah, it's possible that some of these exoplanet systems, so the alkaline exoplanet system, at least sodium and potassium, I wouldn't always say the water. I mean, the water would evaporate very fast. I'm not going to argue that at a hot Jupiter, you've got like something like Saturn's moon Enceladus orbiting it. But sodium and potassium is particularly interesting because if you look at Jupiter's moon Io, most of it is sulfur dioxide. So yeah, metals for astronomers, but 10% of that can be atomic sodium, pure atomic sodium. So that is very high compared to the solar abundance, which is roughly 7 millionths. So that versus 0.1, 5 orders of magnitude higher. So that sort of answers your question, or many questions about that. Why? How could a tiny moon supply an entire atmosphere worth of sodium? Actually, when I was teaching a course at the Indian Institute of Astrophysics last summer, the students did that problem for themselves, and they showed on the board just 5 lines of calculations that you can show because of that chemistry assumption, which is observed in the solar system. A tiny rock can supply all of the metals. So how does it work when you actually simulate this? So that you can do order of magnitude on pen and paper, but now when you simulate it,
Apurva, a quick question.
Yeah,
The previous slide. So, are you suggesting that one of the implications of your work is that the sodium that has been detected in some of the transmission spectroscopy, some of the exoplanets, which is claimed to be from the exoplanet atmosphere, could actually be supplied from the exomoons? Is that what you're suggesting?
yes, that is indeed what I'm suggesting. It could be a mixture, but as I will show now in the next slides, you guys can decide for yourself. So we've only modeled in detail, so the spectrum, maybe 3 or 4 of these dozen systems. There's a dozen or so systems that have very good high resolution sodium and potassium detections. Actually, when I say very good,
Yeah, so basically,
yes.
my question is really, there could be contributions from the exoplanet itself. So how can you tell?
Right. You can tell by just seeing how much the exoplanet contributes to the signal. So let's try it out actually. Oh, maybe this slide is actually good. So how can you distinguish from an atmosphere or an exosphere, first of all, or how can you distinguish between a planet or an exogenic source? So one way is to do this, look at the line ratio between the D2, D1 line, the sodium D2, D1 line ratio is plotted in the y-axis, and the x-axis is the optical depth. Now, if it's very thick, it would be tough to imagine that the sodium is coming from just this small region in the sky due to a moon or this torus. But a torus could supply it if you have it distributed. So you can see that when you look at this, these line ratios, on the top you have WASP 121b, it's very, very optically thin. So the gas you're seeing could be sourced from something very far from the planet. And optically thick, I mean like something approaching like 100 or 10 even, but not, these planet detections don't seem to be so optically thick. And this is actually very fundamental. One can look at papers from Heng and Kitzman, 2017, also in MinRAS, where the geometry, the very geometry of transmission spectroscopy yields a optical depth value of 0.56, so roughly 1. So inherently, the observation should give a gas that is very optically thin. So the entire field of transmission spectroscopy is based on optically thin observations, which are more consistent with exospheres, although we have been interpreting them as thick atmospheres. So let's just try it out. So here we go. Here's some real data taken by HARPS spectrograph in Chile on the European Southern Observatory. I think it's a 3.6 meter telescope by one of my colleagues, Aurélien Wittenbach. So this is our exomoon candidate number 1, WASP-49b. So what you're seeing is the transmission flux and the wavelength. So I'm showing all the dirty data in the back in gray, so you can evaluate for yourself what works. Now, hydrostatic model, this is assuming the planet itself is supplying the sodium. You can see, first of all, that it's very narrow. The significant amount of heating is missing. And second of all, if you look at the left-hand doublet, it seems that it's having trouble reaching that depth. Now, when you do the full calculation of something more reasonable, I would say, hydrodynamic, and again, pump it with 100 times solar, as much sodium as you want, it's actually even worse. The line depth decreases by a factor of 2, and it narrows because the atmosphere actually cools when it escapes. It cannot be heated and give this line. It's due to adiabatic cooling and the Lyman alpha emissions that are observed at exoplanets. And when we try this with an exomoon model, so what I place next is going to be a small exomoon that is just evaporating due to mass loss. It could be from the star or simply from the tidal forces. So either assumption works, and the physical processes can be either plasma-driven atmospheric sputtering or energy-limited escape. Both mechanisms are roughly viable. We actually are able to fit it, I would say, reasonably well. So at present, this system has no explanation of a planetary signature. Now, Fisher and Hang in 2019 did consider non-local thermodynamic equilibrium effects, but as we describe in some of our papers, this model assumes a hydrostatic atmosphere that is just arbitrarily heated just to give the profile that is needed, and then the arbitrary broadening, which they use a parameter called F broad. So when you're modeling, it's convenient to tune your model to give this to give the signature. And so this was in 2019 when we first published our paper, and since then, oh, by the way, yeah, there's a nickname, Mustafar. I'll show you later why that is. Anyways, if you look at HD 189, a more famous exoplanet, you can also see that the hydrostatic and even the escaping atmosphere has trouble getting to the broadening. And if you look on the right-hand side, the D1 line, the depth is just not matched. You can see a D2 to D1 ratio of about 2. And here the outgassing, exomoon, and even the torus fits far better, in my opinion. I mean, you can decide for yourself. Now, a third exoplanet, WASP-121. This was published recently in Heumacher's 2020. And this was in collaboration with the colleague Jens Heumachers, who I work with a lot. He not only found sodium, but magnesium, calcium, chromium, iron, nickel, and even vanadium. I even go back to nickel, even nickel. It's outstanding, the kind of metals they're seeing. And I don't think it's completely obvious to say that it's a planet signature. It could totally be something exogenic from an evaporating body that is otherwise hidden because it's too small. Going back,
Apurva, just a quick question. The planets in question here, they're all hot Jupiters?
That's right.
Typically 1 Jupiter mass or so.
That's right. This planet here, WASP-49, is a third of a Jupiter mass. It's roughly like a Saturn mass planet. But HD 189, I think, is Jupiter mass, and WASP-121 also.
Okay, thanks.
Yeah, thank you. That's also interesting. So you can see, if you can have a very sophisticated outgassing model. So this sort of answers Saurabh's question that what's the chemistry included? You can introduce this chemistry. And so if you follow the blue line, now the blue line has this radial wind shooting out. It even calculates all the vectors in the line of sight, make sure that the subsolar part of the planet is emitting more material. but it simply does not fit the data. And you can see that an optically thin cloud, due to perhaps, in our case, an exomoon or a ring, fits the data better. That's now 3 planets. And yes, once again,
Apurva, there is a question.
Yes.
Pooja Ray, go ahead and ask the question. Oh, but I think she doesn't have a microphone. So. Okay. Well, Saurabh, please go ahead.
Apurva, maybe I'm missing something. So the heating mechanism that you mentioned initially, that was about resonant pumping and then tidal heating.
Right.
So in this case, what is the resonance between? So there is the hot Jupiter, sun, or the star, the moon, and then what is pumping the eccentricity so that the tidal heating keep going on and on?
Right. Great question. And I know that was the title of my talk, but I didn't go into the dynamics as much this time. But that resonant interaction is between the star and the planet, and the moon that experiences this tidal heating. What's pumping it in is actually the stellar tide. So when you do the 3-body problem, you can find that based on the tidal dissipation of the planet and the satellite, so assumptions of this tidal Q, they're very tough to entangle when I ask dynamicists. You find out that a lot of that energy that the star is forcing that would normally scatter the moon is pumped into the moon, and so the moon actually orbits in a resonant fashion that in the calculations that Cassidy et al. Carried out, 1/5 of the planetary period. So in that way, there is some lining up of tides that creates this pumping.
I see. And there is no synchronization, I'm assuming, then, between the planet and the moon, because it's being forced by the star.
Right. Yeah. No synchronization in that sense. So the planet is assumed to be tidally locked. The moon would also be tidally locked, I think. Just the orbit, there's a parameter range of the orbit. It can orbit at 2 planetary radii or 1.5, and yeah. So, but they're not perfectly synchronized with respect to the star. The moon is still orbiting the planet.
Cool.
Yeah, that's a great question, because obviously when I first gave this talk, or when one talks about exomoons, the first thing you talk about is the tides and the gravity. I think last year in Bangalore I gave a talk on that, but this time focusing on the spectroscopy. So great question, thank you. Now, yes, so just ending now. This is very funny. The media picked up this discovery as Darth Vader's birthplace found. I mean, like on the worst news channel of all time, Fox News. But New Scientist even like to say we might have seen signs of an exomoon spewing out volcanic gas. CNN and many other news channels. So it's very interesting. That captivated the public's imagination, because just in one interview, I mentioned that it might be like a moon from Star Wars, Mustafar, because it's actually an exo moon, if you want to be very real and science fiction accurate. So just a fun note to end on. So some conclusions here is that, yes, several alkaline exoplanet systems that have sodium and potassium detections may have been misinterpreted as just purely atmospheres, whereas there are hidden rocky exomoons in that data. And it's been in that data for 18 years. The first sodium detection was by Dave Charbonneau at Harvard, H2209458b. I mean, this triggered the exoplanet era. And I would say at present, exoplanet models fail to self-consistently explain both the spectral line broadening and the line depth. I'm happy to discuss, but I still have not seen one exoplanet model that can actually reproduce both things. And this is just a consequence of high resolution spectroscopy. We are so privileged to actually have this resolution where we can see angstrom shifts of sodium and actually get the dynamics of this sodium. And so follow-up observations will provide this insight. And so some future observations, well, first of all, I'd like to say, I see Athira is in the audience here. She and Dr. Shivrani Tirupati are collaborating with us to analyze some Keck observations from Caltech. And we are looking at the WASP-49 system again with a 10-meter telescope and a much, well, I don't know if it's more stable. We have had a lot of issues getting the alignment up, but it's a very, many more photons will get there and we'll be able to see that sodium. Another nice thing, the VLT, very large telescope, has a spectrograph you may be aware of, Espresso, which gives 10 centimeter per second resolution. And so here we'll really get to see, is that sodium moving? What is that velocity? And you go back to the models we have, we actually predict the speed of the sodium. In fact, it's the speed of the sodium that's causing the line broadening. So that observation, that we have 3 transits, it'll be in October, January and February. And then lastly, if the visible and infrared does not work out, even the radio, which is I think India's bread and butter, even the radio could be useful to find exomoons. And this is in collaboration with Manoj, Ravi Banyal at IIA, Kaustubh Hakim at Bern, and also Mayank Narang here at TIFR. So really excited for these future observations. I think this will really confirm it, or, you know, we'll learn something about the sodium. Maybe it's more like a ring. Maybe the moons are destroyed, but the plasma is around there. And this gives insight into magnetic fields. And you can ask a lot of astronomers. People are magnetophobic these days. We do not use magnetic fields in our exoplanet models. It becomes too complicated. But if I've learned anything from the solar system, is that ions are extremely important and they can be modeled easily using kinetics. So there's no need to have that fear. Last thing I'll say is a sort of, well, okay, one last thing I'll say is that the future of moons and reconciliation with habitability. I'm not this destroyer trying to just make my planets explode all the time. Moons can be interesting for habitability as well. I would encourage people to look at René Heller's papers. They're very nice, where he describes how this is really like mankind's future. Even look at our own solar system. The future, in my opinion, is not Mars, but maybe the Jupiter system, where you can have abundant liquid water. It's no reason to go to dry worlds. These tidal heating mechanisms are actually pervasive. One just needs a little bit of eccentricity and you can get ice worlds to melt. So that's something exciting. And of course, our models can be applied to super Earths and any evaporating rocky worlds. So I hope that can also be used. And then last message I'd say is hidden in plain sight. Now, this is an image I took in the beginning of COVID lockdown, just outside of my window at 5 a.m., just wondering how barren and calm the world is. This sums up our entire theory. Usually, in our field, we've got the most sophisticated 3D models where everyone has 100 parameters tuning it. In very plain, simple message is that here we've got a star which has continuum radiation, and then a sodium cloud. This is a sodium vapor lamp. So if you're looking out at night and wondering, oh man, what was that Oza fellow telling us about exomoons? Well, this is it in a nutshell. It's just that you look at a star and you can see it in another wavelength in sodium, a bright source of sodium. The question is, what is sourcing that sodium? And my answer is exomoons. So with that, I leave you guys, and thank you for this opportunity.
Thank you, Apurva. So we could perhaps have a few questions, if you don't mind. All right. So yeah, there are several hands. So Saurav, I'm giving a chance to others first. So Shivrani, why don't you go first? Yeah.
Yeah, Apurva, it's a nice talk. Yeah, I have just, so when you showed this torus, which is created by this exomoon, so do you assume the density to be uniform across the torus? Or like in the case of Io, you would see like you showed the emission is predominantly coming from the exomoon and it's not uniformly distributed across the torus. In that case, this is could be kind of seen in the transit spectra. For example, would it be seen as an asymmetric line profile, which would be observable?
Yeah, that's a very good question. I'd say I think, okay, so I went back to this slide because here you can see the optical depth, which sort of traces the number density as well. The red line here, you can see that it's roughly uniform out to two Jupiter radii, two planetary radii, and then it sort of drops. So you can see that it's not that uniform. And so the density does change. And I think, yeah, so based on the geometry here, especially this geometry, a torus here, then you would see, even before the planetary transit, you would see a sodium signal.
Okay,
and I think
that
that's
should also be seen in the transit time variation at, for example, in sodium versus some other continuum region, you would see in the transit time ingress that should also be possible, right? Like the transit ingress and egress, if you want to at a continuum wavelength versus at sodium and potassium.
right, exactly that. At ingress and egress, that. I think that's what perhaps won our proposal time, that we mentioned that you should give us the time because we'll be able to tell you if anything is happening before or after the transit in sodium. We just need a big enough telescope because the gas might be tenuous. So hopefully one does see a signal before or after. But if one doesn't mean that there isn't the source. It's just closer to the planet. And that's a good question also because it raises the thing that, I mean, the turbulent problem that what if this moon is so close to the planet and it's just mixed in with that escaping atmosphere? So then what happens is it's even tougher to distinguish. So, but I'd say that, yeah, based on the speed, yeah.
Yeah, thanks, Apurva.
Thanks, Shivrani.
Okay, so Shyama, you had your hand raised, but now I see that you have lowered your hand. But if you have a question, please go ahead and ask. Okay, so Saurabh, you I guess you have additional questions, so please go ahead.
Yeah, Apurva. So these WASP planets, these are extremely close planets with very short orbital period, right?
Yes, yes.
Wondering, has anyone looked at the dynamics of the exomoons and stability and that kind of stuff? Can you point me to the right paper?
Yes, yes. That's how we started this entire problem because, of course, let's see. I have this backup slide. I think this will help. So this is in our 2019 paper. I glossed over it because nowadays, you know, you can capture a moon, so maybe you don't need to form it, but there's this equilibrium tide limit. So essentially, everything in this orange region is tidally stable. But I would say that if the tidal Q factor was much less, 10 to the 6th, and it intersects one of these lines, then the limit would be much, much closer. So Barnes and O'Brien in 2002 assumed that the hot Jupiter's tidal Q should be like Jupiter's. And then, like I had mentioned, Goldreich and Nicholson already previous to that showed that actually Jupiter's tidal Q is much smaller than it should be. The current theory is that Io's orbit, which is much farther out than an exomoon's orbit, is exciting these inertial waves, these convective waves inside the gas giant's atmosphere, which is lowering the tidal Q because it goes as 1 over the energy dissipation. So if you have higher energy dissipation, the tidal Q will be much lower. So that explains that. So tidal physicists, normally though, without that interaction, it should be much higher. And so in that case, all these systems can be tidally stable. Now, a recent paper in 2020, I think by a Japanese scientist, showed that, and we also showed this with another colleague in Switzerland, Emmeline Beaumont at Geneva, that the real problem is dragging in the moons during hot Jupiter migration. During the migration, it's possible that the moons would be scattered. So I would agree with anyone that is saying that these systems should be rare based on formation and migration. But that's not to say that they're not there. I mean, there's from 3,000 exoplanets, I would say at least 10 systems could be possible, and especially given the sodium and potassium detections not being one-to-one. Not every hot Jupiter has a sodium atmosphere, actually. So yeah.
Yeah, I will also point out that so if you have a gaseous planet and that collides with some other gaseous planet, then under certain configurations, they will just not merge, and they potentially can create a binary planet.
Mm.
So it was kind of curious that there was one example you showed that's not really a moon, it's more like a binary planet with some mass. So that's another potential formation mechanism. But I do agree that they will still be rare.
Oh, great. That's nice to hear. Yeah, I think once people, yeah, go ahead.
You take a look at Huang et al., Huang, Chatterjee, and Rasio a few years ago.
All right. Okay. I'd be happy to look at that. Right. Yeah. I think there's many unexplored formation pathways. I mean, look at our own solar system, the Nice model. Well, this is just banter from Bern, but many people call this one of the most fine-tuned models in physics. So to get everything precisely right, to form everything, it requires lots of very specific scenarios. So, I mean, planet formation, moon formation for that matter, is tough to reconcile. So I'd say there's a multitude of different processes that can form a moon even close in. Yeah.
Okay, so Mayank, go ahead with your question.
Hey, Apurva. So,
Hey,
quick question. Given that there are a couple of ways in which we can more or less postulate that there is an exomoon, what do you think would give us an unbiased kind of detection? Like in
right.
radial velocity or transit there.
Right.
So but direct imaging is like this one method which says that, yeah, there is a planet. But earlier on, there was this contention that whether the radial velocity signatures that we are detecting or the transit signatures that we are detecting are then due to the planet. Is there a method by which we can be 100% sure that the signal is from an exomoon?
Right. So, well, we published our result in Astrophysical Journal mostly so we can describe all the physics, although we were, reasonably confident that WASP-49 may have this exomoon. So yeah, having this claim might be the next step. So I'd say when you go back to here, it really comes down to this model.
Yes.
It really comes down to the physics. So one has to really stick with the physics so that no matter how much you put into the exoplanet itself, you cannot create this quantity of sodium, because luckily spectroscopy gives you the minimum line of sight column density. So if that minimum line of sight column density is not reached with reasonable assumptions, then I think you can unambiguously say that a very large source of sodium is missing. And there, I think, yes, could you say moon or ring? So at least you've gone that it's not the planet. So now you've made the claim that it's an exogenic source. But I think really looking at this in more detail, like we're trying to do with other telescopes, and seeing exactly how that sodium is behaving, repeating the observation, I think that's all good to make a stronger claim. I would say that I think what will make most of the community satisfied is one of the more classic methods like radial velocity. So I am working with a colleague in Paris, Sébastien Charnot, who has discovered moons of Saturn using his own method. And we're using that same method to look at exoplanet systems. So perhaps that will be much more unambiguous, because what's the definition of satellite? Something that is orbiting, so it has a periodicity, and people want to know the period of these moons. So if you can get the period of the moon, I think that'll be smoking gun.
I have a quick question about this particular figure, actually. So it looks like the points right before egress and right before ingress and right after egress on both cases have a little more than what you'd expect. Is that real?
So this isn't a time series, though. This is against wavelength, so it's not ingress and egress. It's it's averaged. But no, good eyes, because you are noticing some interesting stuff that now if it's shifted, it means that the sodium has a velocity to it. So it's a slightly offline center, possibly. So asymmetric profile, I think, yes, as Shivrani was also implying, that the spectral feature can create an asymmetry due to the geometry of the cloud.
Other questions? Apurva, I have a quick question. Can you go back
Please.
to the conclusion slide? So you had the 3 conclusions, and I have a question on one of them, which is, the second point. So you seem to be arguing that at least for the alkaline lines that have been detected in the exoplanet and from transmission spectroscopy, exoplanet alone cannot account for it, right? But there are other lines that are also detected from transmission spectroscopy. How about them? So are there other lines which can entirely be explained by exoplanet atmosphere?
Yeah, right. So the question is, this new age of high resolution spectroscopy. So so far, let's see, Jens, for example, I'd encourage you to look at his papers. Oh, sorry, I didn't even write his name, but it's Hoijmakers, Hoijmakers, Hoijmakers. But he has a series of papers with these metal lines that cannot be explained entirely by the exoplanet. Oh, perhaps you are aware of this Nature paper, 2018, where they found atomic iron and titanium in the exoplanet atmosphere. So those, for the planet Kelt 9b. So that's one example of where it doesn't work. But I would say the Lyman alpha observations, which for a decade almost, that does seem to be explained by an exoplanet. And
helium lines.
Yeah, and the helium lines. Also, I think there are some issues, again, with maybe using local thermodynamic equilibrium assumptions. But
the largest, so would you say the largest discrepancy is in the metallic lines?
Yes, absolutely. And I think that's, it goes in the right direction, right? You would expect the moons to give you metals or rocky bodies if one feels uncomfortable calling them moons. But the hydrogen and helium natural sources, the gas giant, you have a giant gas tank sitting there. So I'd say I wouldn't go as far as refuting those claims. I'm sure, I mean, the only thing I'll say is that, once again, moons can also supply a lot of hydrogen if they're icy moons, but I wouldn't expect them to survive for too long out here. So yeah, I would say that those discoveries are our sound.
Okay, thanks. Other questions? If there are no more questions, let's thank Apurva once again for an exciting talk. Thanks, Apurva. Thanks for your time, and thanks for waking up early for us.
Thank you very
And
much.
I will
It was a
applaud.
pleasure. Yes. All right.
On Elsa's behalf.
Feels nice virtually. I can't hear anything. So good. Thank you very much.